Hi everybody, this is Lynette again. Forgot to put the recorder on the Adobe Connect session, so I thought I'd do another YouTube video. Okay, what I'm looking at today is just two questions, one out of 2014 past exam paper and one out of 2013 T3 past exam paper. Oh, the 2014 was a trimester 2 paper. Okay, so what I'm going to do first is look at one of the multiple choice questions in T2 2014. Now that paper was actually sat in January of 2015. And the question I'm looking at is question 1, which was multiple choice questions, part 2. And I'll bring that up and we can see the question. The question says, oh no, I've got the wrong one. The question says, weight is a measure that tends to be normally distributed. Okay, so what do we know? We know that weight follows a normal distribution. And we're told some things about that normal distribution. We're told that the mean weight of all women at a large university is 67 kilograms. So it has a mean of 67 kilograms. We're also told that the standard deviation for that is 6 kilograms. If we took a random sample of 36 women from this population, what would be the 68% chance that a sample mean weight would be between two values? So we have to find basically a confidence interval for around the mean of 67 with one standard deviation either side of it. And why is it one standard deviation? Well, if we have a look at a normal, just a general normal distribution, the middle point is our mean. And if we're just using this as a Z scale, so using Z points, this is 1, 2, 3 standard deviations away from the mean. This is -1, -2, -3 standard deviations away from the mean. And we know that if we go one standard deviation either side of the mean, then that covers approximately 68% of our information. So in other words, we want to find these end points. So how do we do that? And notice also we want it for a sample, not just an ordinary standard confidence interval. So because of that, we need our confidence interval basically is going to plus or minus 1. We want these endpoints that are plus or minus 1 standard deviation. But with samples we work with standard errors, not standard deviations. So we want our sigma, that's a sigma not a 6, over the square root of n. So this will give us 67 plus or minus, well we can leave the 1 out now. Our standard deviation original for the population was 6 and our sample size is 36, so we do that. So that would be 67 plus or minus 6 over, and the square root of 36 is 6, so that gives us 67 plus or minus 1, which means that our confidence interval is going to range between 66 and 68 kilograms. So we expect that the mean would lie, the sample mean would lie somewhere between 66 and 68 kilograms. Right, That was the last option on the question. Let me just check. That was part D. So that was answer D for that question. Right, so that was working on that. The next question somebody asked me about, and it was Ian, was from the T3 2013 paper. Oh, sorry, no, T2 was not January 2015, it was October 2014. I'm getting my T2s and T3s mixed up here. So T3 paper, that would be in January 2014. Okay, and what Ian was asking about was question 7. And this was about analyses of variances. So, let's have a look at, I'll just read the question. I'll just go to where it is. And what we're told about this actually goes over a couple of pages, so just let me scroll up to it. We've got 8 trees were grown on each of 5 types of rootstock in an apple orchard grafting experiment. Okay, so we have 5 groups. 5 rootstock. So I'm unpacking the information, unpacking the question. 5 rootstock groups, and there was 8 repeats. Within each group. The extension growth in metres, in other words from the height at which they started from to where they were after 4 years, for each of the trees was recorded. And then they were presented with a dot plot, not a box plot but a dot plot this time, in the question. And then they were also presented with a summary statistics table giving the mean and the standard deviation for each of those 5 rootstock groups. The first part of the question presented the students with a part of an analysis of variance table, and they had to calculate the missing F statistic. So I will draw on the paper what they were given and show you how to fill in the rest of it. So, on my table, we have a degrees of freedom. Our groups was called rootstock, and then we have the residuals. Now, sometimes the residuals are called error. Okay, it just depends on your teacher. It depends on the degree, on the computing program that you're using. Also, it could be called within groups. I'm of the old school, and we were called between groups. That was our groups there, and this was information about our within groups. Okay, degrees of freedom. Well, we had 5 rootstock groups, so our degrees of freedom for the rootstock will be 5 minus 1, which is 4. Now, the total, we'll put another line under there and just put total. Our total degrees of freedom is the total number of trees that were there, that were used no matter what group they belonged to, minus 1. So the total number of trees is 8 times 5, which is 40, and 40 minus 1 is 39. So our total degrees of freedom is 39. Now, like in everything, 4 plus x equals 39, and that would give us 35. The other way of finding the degrees of freedom for the residuals group is say, well, our total number is 40, and we have 5 groups, so 40 minus 5 is 35. The other bit of information that was given was the sum of squares, and we're told that that was 1.36 for our rootstock and 9.03 for our residuals. We don't need the total. Now we have to find F. How are we going to find f? Well, to find f, we need our mean sum of squares. How do we find that? We take our sum of squares and divide it by 4. Mean is an average, so it's like finding an average. Except we don't divide it by 5, we actually divide it by degrees of freedom, n minus 1. 1.36 divided by 4. So on my calculator, good old trusty calculator, 1.36 divided by 4 equals 0.34. And we do the same for our mean sum of squares for residuals. 9.03 divided by 35 is equal to 0.258. Okay, so how did I find my mean sum of squares? I took my sum of squares and divided it by its group degrees of freedom. Okay, now how do I find my f? My f statistic is another division. This time we take the mean sum of squares for our group, which is our root stocks. So we've got 0.34, and we're going to divide that by the mean sum of squares for residuals, which is 0.258. So I've got 0.34 divided by, this up so you can see it, get it in the spot where you can see it, divided by 0.258, which is equal to 1.32. Have I got the right numbers? Yes. Okay. So we've now got our f value. I don't know why I wrote it down there. Okay. So that was the f value. That was for part A. We were then told, given in the table, that the p-value for being greater than f, just checking something, yes, probability greater than f, was equal to 0.28. Now, the degrees of freedom for that probability, if you needed to look it up at any time, are the 2 degrees of freedom, your group and then your residuals. So this 435. We have a p-value of 0.28. The second part of the question, so we've finished the table. The second part of the question asked to test for a difference in the mean extension growth among the 5 rootstocks. Well, I'm going to turn the page, take a new page, because what we're going to do first of all, to be able to test for a difference in extension, we need to test some sort of null hypothesis. So what is our null hypothesis this time? It's an analysis of variance, so we've got more than 2 groups. So, and our null hypothesis in general says that there is no difference or things are the same. So what are we looking at here? The mean growth extension for all 5 rootstocks is the same. Now if you wanted to put that in symbols, you would have, they were just labelled 1 to 5, so mu1 equals mu2 equals mu3 equals mu4 equals mu5. So that's the null hypothesis. The alternative hypothesis would be that at least one rootstock group has a difference in mean growth extension. that across so you can read it all. Okay, because that covers a lot of different possibilities. We could have only one different, we could have them all different, we could have some equal to but those two subgroups not being equal. We don't use symbols to define our alternative hypothesis. We leave it in words. Okay, well, we've carried out the test. We found out in our previous part that f was equal to 1.32 and we had a p-value of 0.28. So what's our decision rule? Our decision rule asks, is p greater than 0.05 or is p less than 0.05? So what have we got? Well, we've got a p equal to 0.28, and that is definitely greater than 0.05. Right? So what does that mean? So what we can say is that the mean growth, there appears to be no difference in mean growth extension between the 5 groups. Because the information we've got supporting the null hypothesis, and the null hypothesis was that the mean growth extension was the same. So we can answer the question. It said test for a difference in mean growth extension among the 5 rootstocks. So we need to conclude in terms of that. So there appears to be no difference in mean growth extension between the 5 groups. Okay, now part C, which is something we probably should have done when we were carrying out that test, but it's asked for a specific spot here, so we may as well look at it here. It says state the necessary conditions for the test. With reference to relevant output, check as many of those assumptions as possible. Okay, well, what are the assumptions that we need? Well, assumptions. Or conditions. Okay, the first one is no extreme outliers. Now these are something that you should be putting down on your study sheets that you can take into the exam with you. I did suggest that in the previous video, that when you write down what the different types of tests are that you can do in a hypothesis test, that beside them you write down the conditions that are supposed to be met to allow you to carry out those tests and therefore have confidence in the results that you get from them or the conclusions that you get from them. So no extreme outliers. Now what information have we got? Well, normally we'd look at box plots, but we were given dot plots. Well, that does just almost as well. So I'm just going to flick back. Now you can't see this, but I'm going to flick back and look at the dot plots that we were given. And the dot plots we were given, they're reasonably consistent. They're not too spread out. There appears there may be an outlier for rootstock 2, but it's not that extreme. I think if we did a box plot, we'd find that it was probably close to the bottom whisker. So it's not too bad. So no extreme outliers. So what we'd need to say is that using, now that was in the exam paper, that was called figure 3. Using figure 3 dot plots, because you need to refer to where you're getting the information from. Using figure 3 dot plots, all groups appear reasonably close together with group 2 may have, my English is not the best, appear reasonably close together with group 2 may have an outlier. However, this does not appear to be extreme. So it's not too far away from all the rest of them. Okay, so it also shows us that the distributions do not appear skewed. Now, not an overall distribution, but the distributions for each group do not appear to be skewed. So they're approximately normally distributed. Okay, the second condition we have to have, I'll move my piece of paper up a bit more, is that the standard deviations have to be approximately the same. Now this follows through from your pooled t-test. In the pooled t-test, we took our largest standard deviation and divided it by the smallest one, and then we compared that with the number 2. So we said if it was less than 2, then we could say they're approximately the same. Well, we do exactly the same thing here, except, well, we've got more than 2 standard deviations. In actual fact, in this question, we were given 5 because there are 5 groups. So what we do for an analysis of variance, we take the largest standard deviation and divide it by the smallest one. And in this case, these were 0.607 and 0.393. Now, if we work that out on the calculator, that gives us approximately 1.54. We ask ourselves, is this less than 2? Yes. Therefore, we can say that the standard deviations are approximately the same. If we did have a slightly skewed or some slightly skewed distributions, and therefore some outliers, as long as n was reasonably large, 20-ish or more, then an analysis of variance test is a bit lenient and can cope with that kind of skewness. In this case, I don't think we needed to worry about that. So they were the 2 conditions, and we had information. The standard deviations are approximately the same. That information came from table 4. So I used the information in table 4 that was given to be able to determine that. So that was the answers. That were the answers for 2 questions. The first one was a multiple choice question, so it was very quick. Couple of minutes working on that one at the most. This question was a bit bigger. It was one of the longer questions. It was worth 6 marks, so approximately 12 minutes to answer that, and that was quite easily done if you knew your work and if you had information on your study sheets to help you do that. Like, for instance, you didn't have to think about the conditions because you had them written down. No extreme outliers, approximately nothing appearing skewed, standard deviations approximately the same. If you remembered how to write an hypothesis, and again, under your subheading of analysis of variance on your study sheets, you could have done a general equation there. mu1 equals mu2 equals mu3 ... depending on how many groups you've got, so that the mean growth extension for making it specific to this question, the mean growth extension for all 5 rootstocks is the same. And the important one to remember is at least one rootstock group has a difference in mean growth extension for your alternative, and don't try to use symbols for that. Okay, so that is a quick run through and a revision on 2 topics. First of all, a revision on your normal distribution and what does 68% and so forth. And remember that 2 standard deviations is approximately 95%, and 3 standard deviations is approximately 99.7% of information is held within 3 standard deviations of the mean. So, and then analyses of variances, a run through of analyses of variances. Okay, so thank you very much for watching, and I'll see you on another one sometime. Bye.